Hello everyone, I'm Yizhi from Hunan University. I will present our work, a novel multi-CPU GPU collaborative computing framework for SGD-based matrix factorization. This is a joint work with Zhejiang Lab. Matrix factorization is widely used in recommendation systems. As shown in the figure, the user's rating of the item can be coded as a rating matrix R. Matrix factorization will decompose R into a user matrix P and an item matrix Q, and then the product of P and Q can be used to predict unknown ratings in the rating matrix. Using SGD algorithm to solve matrix factorization is called SGD-based MF. In SGD-based MF, every time a rating is processed, it is necessary to calculate a root mean square error and two vector updates, including multiple vector product calculations. When there are many ratings, SGD-based MF can be very time-consuming. Therefore, many researchers have used distributed systems, CPUs, GPUs, and multiple GPUs to accelerate SGD-based MF. Currently, there are usually multiple CPUs and GPUs in the same computing node. GPU has far more computing power than CPU, and the management of the same type of processor is easier. Therefore, researchers prefer to use multiple GPUs to accelerate algorithms. CPU is only used for logic control or submitting GPU tasks. Its computing utilization is not high. However, modern CPUs have integrated more cores and also have strong parallel capabilities. At the same time, some recent studies have shown that for the SGD algorithm, the CPU can also provide good acceleration. We tested SGD-based MF on different CPU and GPU. We found that the performance growth of high-end GPUs is not linearly related to price growth. Then, we tried to use a CPU and a GPU to joint calculate SGD-based MF. We found that its performance was close to that of a better GPU, but the price-performance ratio is much higher than a better GPU. Based on these two observations, we considered adding CPUs in system to collaborative computing SGD-based MF with GPUs. In a multi-CPU GPU computing node, the CPU and GPU are heterogeneous, and GPUs can also be heterogeneous. We perform naive collaborative computing on a CPU and GPU. It can be seen that bad data distribution and poor communication design will greatly reduce the efficiency of the system. Bad data distribution will make light-loaded processors wait for heavy-loaded processors. For a CPU and a GPU, we can easily adjust the load manual to make them run under appropriate load. However, it is difficult to manually adjust the data distribution on more heterogeneous CPUs and GPUs. In addition, we find the communication overhead is so great that can offset the benefit brought by collaborative computing. Therefore, for collaborative computing, we must face these three challenges. First, how to uniformly manage and transparently use heterogeneous CPUs and GPUs. Second, how to design appropriate data distribution. Third, how to optimize communication inter CPUs and GPUs. Next, I will show our design and implementation. We designed a collaborative computing framework named HCC-MF and addressed these three challenges. HCC-MF uniformly abstract heterogeneous CPUs and GPUs, and calculates SGD-based MF collaboratively in a unified workflow. HCC-MF has a worker-server structure, similar to parameter server. To manage and use CPUs and GPUs in a unified manner, we abstract them as worker processes that proxies different execution kernels, such as Hogweird, FPSGD, CU-MF SGD. We use share memory as a communication channel. The pull buffer on the server will be mapped to all workers, and the push buffer on the workers will also be mapped to the server. The server assigns data to workers according to the data partition strategies. Workers will train SGD-based MF asynchronously. The training process is abstracted into a loop: pull, computing, push, and synchronization. Next, we will introduce our data partition strategies. To solve the data distribution problem, we have established a cost model to guide that distribution and propose two data partition strategies to deal with different synchronization conditions. According to the training process of HCC-MF, the training time of each round is composed of the longest execution time of all workers and the subsequent synchronization time on the server. We can use time and space complexity, runtime performance, bus bandwidth, memory bandwidth, and other parameters to model time overhead. Theoretically, the value of computing performance is much larger than the bus bandwidth. Therefore, we omit the performance-related components and finally get the equation. More importantly, we found that synchronization overhead and communication overhead are similar in size. Compared to computation overhead, maybe they can be ignored. In the end, we obtain a piece function about data distribution and use it as the objective function. We first solve the case where synchronization overhead is not considered. At this time, the objective function theta is as shown in the formula. To simplify the calculation, we assume that the memory bandwidth is always a constant function of data distribution. Then, the objective function can be simplified to the min-max form of the linear function. In this way, we can use monotonicity to easily prove that when the execution time of each worker is balanced, the total overhead is minimal. Since the communication overhead is small, they can be considered equal. Now, we get the data partition formula and obtain the value of data partitions through the execution time information of each worker. We call it dp0, but can dp0 really guarantee load balancing? On one hand, the assumption that memory bandwidth is constant function is not entirely true. Bandwidth is more sensitive to the amount of data on GPU. On the other hand, the performance during actual execution cannot be ignored, especially on GPU. Therefore, as shown in the figure, in actual execution, dp0 doesn't guarantee equal execution time. We must fix the data partition. We refer to the idea of differential, and then design algorithm 1. If delta x is small, delta t can be regarded as linear. The data partition of dp0 fits this condition very well. We use dp0 as the input of algorithm 1 to obtain data partition for load balance named dp1. Next, we solve the situation that needs to consider synchronization. The t in the synchronization component in the formula is a non-linear function of the data distribution x. The existing constraints are not enough to find the solution to the objective function. Therefore, we adopt a best effort approach to keep the time overhead as small as possible. First, distribute the data according to dp1 so that the yellow box part is minimized. Secondly, taking the execution time of dp1 as the input of the formula in the green box, a new data distribution dp2 is obtained. In this way, the calculation time is used to hide the synchronization time to reduce the total overhead. To optimize communication, we have designed 3 communication strategies from the perspective of reducing data transmission and overlapping communication. We have observed that users are independent of each other. That is, the rows of rating matrix are independent. Therefore, the training process only needs to transmit the Q matrix, and the P matrix can be calculated locally by each work. In addition, the recommendation systems usually use 100-point systems, 10-point systems, or 5-point systems. IEEE FP16 can completely cover all numeric representations. Therefore, we use FP16 format to transmit data. Inside the worker, we have established a pool computing push pipeline. These streams are executed asynchronously, and the calculation of the current stream can be used to overlap the transmission of the next stream. The current hardware is sufficient to support this design. For example, we can use copy engine on GPU, use multi-threading and free memory bandwidth on CPU, use copy engine with integrated GPU on SoC. Next, I will introduce the evaluation of HCC-MF. The specific evaluation settings are as follows. First, we discuss the overall performance of HCC-MF. HCC-MF will synchronize all workers in each epoch. Therefore, parallelism will not affect its convergency rate, which is consistent with the convergency rate of the algorithm on a single processor. The training speed has been improved. Among them, the improvement on Netflix and R2 is larger, which are 2.3 times and 2.9 times of GPU respectively. Second, we introduce the impact of data partition strategies on performance. For datasets that don't need to consider synchronization overhead, such as Netflix and R2, DP0 can only guarantee the balance between simultaneous processors, while DP1 can guarantee the balance between heterogeneous processors. On these two datasets, the overall cost of using DP1 will be reduced 12.2% and 10% compared to using DP0. For datasets that need to consider synchronization overhead, R1 star, DP2 can effectively hide the synchronization overhead, and total overhead is 12.1% lower than that of DP1. Comparing COM and COM-P, it can be seen that the performance rules of the communication strategy is regardless of the implementation. Q can achieve better performance, but the effectiveness depends on the shape of the rating matrix. The transmission performance of half Q is more than twice of that Q. This may be because the combined data transfer will bring better performance. HCC-MF is the first heterogeneous multi-CPU GPU collaborative computing framework for SGD-based MF. It has a unified workflow and can transparently use heterogeneous CPUs and GPUs in the system. Its two data partition strategies can deal with different synchronization overhead situations, and it provides a series of effective communication optimization methods. However, it currently has some limitations. We have already started follow-up work on these limitations. That's all of my presentation. Thank you very much.